Comment on the effect of the following matrices on vectors when they are multiplied into the vectors. Illustrate your response by examples. I'll start with A. Rx is 1, 0, 0, minus 1. Rx is responsible for reflection about the x-axis. For example, if we have a point, or better say a vector, such as A, which is, let's say, 1 and 2, this vector upon reflection about the x-axis, we expect the x-coordinate of A would not change, but the y-coordinate of A would be multiplied by a negative sign. Therefore, we expect A to become A prime, which is 1 and minus 2. Let's see if Rx does the job for us. Let's multiply Rx into A and see what we obtain. Rx into A is 1, 0, 0, minus 1 times A. This is 1 times 1 plus 0 times 2, 0 times 1 plus minus 1 times 2. And if we simplify this, it becomes 1 and minus 2, which is actually A prime, as we can see. So we showed by an example that Rx reflects a vector about the x-axis. You can try other examples to show the same effect. Let's now look at B. Ry is equal to minus 1, 0, 0, and 1. It is responsible for reflection about the y-axis. Let's consider a vector A, let's say 1 and 2, the same example that we used before. If we reflect A with respect to the y-axis, we expect to get this vector. We expect the x-coordinate to be multiplied into a negative 1 and the y-coordinate to remain the same. So we expect that A under reflection about the y-axis becomes A double prime, which is minus 1 and 2. Let's see whether Ry can do the job. Ry times A is equal to minus 1, 0, 0, 1 times A, which is 1, 2. This becomes minus 1 times 1 plus 0 times 2, 0 times 1 plus 1 times 2. And this is equal to minus 1 and 2, which is indeed equal to A double prime. You can try other vectors and verify that if you multiply those vectors by Ry, you would get new vectors which are the reflection of the original vectors with respect to the y-axis. Let's now look at C. Ro is minus 1, 0, 0, minus 1. This is responsible for reflection of a vector about the origin of the coordinate system. And that's why we use O for the subscript. Now let's consider again the vector A, which is 1 and 2. If we reflect this vector about the origin, we would expect to get a vector, let's call it a triple prime, with the coordinates minus 2 and minus 1. Let's see whether RO can achieve this. Let's multiply RO into A. This becomes minus 1, 0, 0, minus 1 times 1 and 2, which is equal to minus 1 times 1 plus 0 times 2, and for the y coordinate 0 times 1 plus minus 1 times 2. And if we simplify this, we get minus 1 and minus 2, which is indeed equal to a triple prime. You can show that RO is actually Rx times Ry. It is also equal to Ry times Rx. What this means is that reflection with respect to the origin is the same as reflection with respect to the y-axis followed by reflection with respect to the x-axis. Also, it is equal to reflection by the x-axis followed by the reflection with respect to the y-axis. And this makes sense intuitively. Now let's look at case D. R theta is cos theta minus sine theta and cos theta. R theta is responsible for rotation of a vector about the origin by an angle theta. In other words, if we have a vector, let's say A here, if we multiply A by R theta, we will get a vector which has the same length as A, but it has rotated by the angle theta. Let's call that A prime. A prime is R theta times A. Let's now look at a particular example. Let's consider the vector A with the coordinates 1 and 1. From the Pythagorean theorem, we know that the length of this vector is root 1 squared plus 1 squared, which is root 2. Therefore, the length of the vector is root 2. And we also know that this angle as well as this angle would be 45 degrees. That means that if we rotate this vector, which we called A, by 45 degrees, we would get a new vector, A prime, which has its length equal to root 2 and its angle with the x-axis 90 degrees. The x-coordinate of this new vector is therefore 0 and the y-coordinate is root 2. Once more, if we rotate the vector A by 45 degrees, we expect to get the vector A prime with the coordinates 0 and root 2. Let's see whether our 45 degrees can do this job for us. We multiply our 45 degrees by A and see whether this will be equal to A prime. R 45 degrees times A is equal to cos 45 degrees minus sine 45 degrees sine 45 degrees cos 45 degrees times A, which is 1 and 1. Cos 45 degrees is root 2 over 2. Sine 45 degrees is also root 2 over 2. So we can sub for cos and sine in terms of their values, and we start multiplying the two matrices. Root 2 over 2 times 1 plus minus root 2 over 2 times 1 for the x-coordinate, and root 2 over 2 times 1 plus root 2 over 2 times 1 for the y-coordinate. We can simplify this to 0 for the x-coordinate and 2 root 2 over 2 for the y-coordinate, which if we simplify becomes 0 and root 2. And this is indeed A prime, as we explained above. These matrices Rx, Ry, Ro, and R theta, and many more, have a lot of practical applications in robotics, in particular in rotation of the robotic hand. There are more extended matrices, 3 by 3, which are used for the rotation of the robotic hand in 3 dimensions, much the same as the identity Ro is equal to Rx times Ry, which is equal to Ry times Rx, which expresses the fact that reflection with respect to the x, and after that y-axis is equivalent to the reflection with respect to the origin, has also some counterparts for rotation. R theta times R theta prime means rotation by theta followed by rotation by theta prime. In other words, a full rotation of the magnitude theta plus theta prime. This identity is directly related to many trigonometric identities.